So first one should be easy. Definite integral from 2 to 7 of f of x dx is just the area under that line. We end up with that blue rectangle. So it's 3 times 5, we get 15. Now, if we take that rectangle and we have that attached to the x-axis and spin it around the x-axis, so this part is kind of stuck there, and this spins around. Think of it like if it spins really, really fast, what kind of shape does it look like? Cylinder. The end looks like a circle, but the whole thing is a cylinder. All right. Now, volume of cylinder is just pi r squared times height. So the radius here would be 3. The height would be 5.
That's what I thought already. I thought you meant it comes out. Like, how we can find the volume?
All right. So that kind of leads us to what we're going to start doing in this section. Last section we looked at just area between curves. Last chapter we looked at area under a curve. So like this first part here, I'm frozen. There we go. This first part right here, the area under that curve, we could do, if we knew the functions, just the definite integral from a to b of f of x dx, right? And we would basically do that using, like, technically we would have used rectangles to find the area. That's kind of what our definite integral does, is finds the limit as the number of rectangles approaches infinity. We went through all that process a long time ago. Well, if we take that shape and spin it around the x-axis, we end up getting this like bell-shaped graph. So we're looking at finding the volume of this kind of a shape, or something that's revolved around an axis. So this volume is called a solid of revolution. And if I were ever to have a band, which I probably won't because I don't know how to play any musical instruments, but if I were to have a band, this would be the name of my band. This next term, calculus term, axis of revolution. I think it's a great math band name. All right, axis of revolution, the x-axis. That's what we're spinning that shape around. So if you ever hit it big with the band, make sure your name is Axis of Revolution. Put me in the credits on your CD. Alright. So if we kind of break this down, that first curve, like I was saying, back when we started with rectangles, and we worked our way to like the sum of all the rectangles, the limit of the sum, to find the definite integral that gave us the exact area. Now, we're not going to go through that whole process for volume, but it's basically the same thing we dealt with before. So if we look at like one rectangle here, so if we focus in on this one, if we take that one rectangle and spin it around the x-axis, we get a cylinder. All right? We get a cylinder right there, and that cylinder, in this case, it's kind of a flat cylinder, not very tall, and what we are going to call this cylinder is a disc. Now we're going to look at 3 different types of cylinders to find volume. Today we're focusing on discs. The other 2 we're going to talk about are shells and washers. They both kind of have cylinders with holes in them. So we have to kind of take into account how they look in these different shapes. So this is just a disc, a solid cylinder, but it's kind of like a short, it's kind of on its side right now, but like the thickness or height is kind of small, and that's dx in this case. And then the radius of that function is just going to be the height of this rectangle. Right? The height of that rectangle is the y value of the graph, or the function in terms of x. So this cylinder, kind of like the one we did before, has the same volume. It's just pi r squared times height. So to find the volume of this whole shape, like using cylinders, now if we went back and did it from the very beginning, we would have to do like the limit as n approaches infinity of the sum from k equals 1 to n of all of those volumes. So the volumes are just going to be pi times the radius, which is our function. So we can say f of w sub k squared times the height of the cylinder, which would be delta x sub k. Right, that big ugly formula gives us the exact volume. But just like before, we're not using that big ugly formula. We have definite integrals that kind of take this and simplify it for us. We're taking the definite integral from a to b of pi times the radius squared. Well, the radius is just the function in terms of x times the height, which is dx. And so this is still the same as pi r squared times height. It's just taking the sum of all of those rectangles as the number of rectangles approaches infinity. So this formula right here is the volume using disks and this is for when we go around the x-axis.